discussion on geotechnical earthquake engineering, also known as soil dynamics. Why this is important means we'll be having a introduction of this subject, that what is this subject, why this is important for civil engineers, and you will get an opportunity to study this. Why you should take that opportunity, because so we will have a brief look on the subject, and at the end, I hope at the end of the session you will be able to grasp the importance of the subject itself. Okay, so let's start with the subject. So, thing is, what is earthquake engineering? Then, if we understand what is earthquake engineering, then only we can understand the importance of geotechnical earthquake engineering, which is one step further. So, when we are talking about earthquake engineering, what is earthquake? Means why this is earthquake is important. So, whenever we talk about earthquake, we get a feeling of risk. There is risk. So, what is risk? When we talk about risk is a combination of three different components. First is hazard, another is vulnerability, and third is the value. There must be some hazard. Okay, there must be some hazard. There is a potential hazard. If you are over a lake, then there is a hazard that if somehow that boat sunk, then you have a hazard that you can drown if you don't know how to swim. The vulnerability, the drowning is the lake is a hazard because it possesses a hazard that you can drown in the lake. Now, what is the vulnerability? Vulnerability is your boat and you. If it is weak, it may break. That is one vulnerability. Another vulnerability is you don't know how to swim. If you know how to swim, then the vulnerability is zero. There is no risk. But if you don't know how to swim, there is vulnerability. If you don't know how to swim, but your boat I got muted. If the boat is good, it is competent, then again the vulnerability is zero and the risk is zero. So this is how hazard and vulnerability is defined. Now, what is value? Your life has a value, and when we talk about the value, we talk about the insurance. Okay, so the value is not of much importance for the engineers per se, but hazard and vulnerability is our area of the are the terms which are related to our area. So when we talk about the hazard in our case in earthquake engineering is earthquake. Earthquake can cause damage to buildings. And when we talk about this hazard, the earthquake hazard, the engineering seismology is a subject which helps us to understand this hazard. Engineering seismology is a subject which helps us to understand the hazard. What kind of earthquake can come, what kind of earthquake, how big it could be. Like this, there are different kinds of earthquakes. There are major causes of earthquakes are tectonic movement we have in Himalayas every now and then. And the most recent big earthquake was the Gorkha earthquake near Kathmandu in 2015, I think, April 25th, and then 12th May. These two dates were there. So tectonic movement is a major cause of earthquake. Volcanic eruption is a major cause of earthquake. Landslides may cause earthquakes, because earthquake, when we say earthquake means rapid movement of ground, rapid shaking of ground. So landslides may cause earthquake. Another very important thing which may cause earthquake is reservoirs. The very famous example of reservoir-induced earthquake is Koyna Dam in Maharashtra, which caused a big earthquake in 1960s. And after that, each and every dam should be equipped with lots of seismographs, so that any seismicity which caused by these reservoirs should be studied if they are causing any seismicity or they are inducing any earthquakes. Nuclear blasts, of course, can cause earthquakes. So the hazard, these are the hazards. Okay, and engineering seismology helps us to understand this hazard. Now comes earthquake engineering. Earthquake engineering is a subject which helps us to build the buildings which can sustain, which are not vulnerable when the hazard comes. When the hazard comes, you have a good boat, you know swimming, like this. So if you have a well-engineered building, well-designed building, then even if you have great earthquake, the building will not fall. And if it won't fall, and there is not much loss to you. Okay, so there might be some losses to the building, but your life will be saved. So the earthquake engineering helps us to design proper buildings, proper structures, which will not be vulnerable in any hazard, in earthquake hazard. So the earthquake engineering seismology helps us to understand the hazard. We can't overcome the hazard as when we are in the boat. We can't escape the lake. But what we can do is we can learn swimming. We can have a good boat. Okay, so we can't do much about the hazard, but just one thing we can do is we can understand the hazard. But what we can do is we can reduce our vulnerability. When we are talking about reduction of vulnerability, then comes the earthquake engineering. And when vulnerability is reduced, the risk reduces. Okay. The after effects of earthquakes are landslides, rock falls, tsunami, subsidence and lateral spreading, liquefaction, collapse of structure. These are the after effects of earthquake. And when we talk about the earthquake engineering, it helps us to the vulnerability due to these effects. Now let's discuss something about the origin of earthquake. When in 1900, in the start of 1900s, a thought came that Earth is made up of plates, different plates, and to be precise, the 7 plates are known. The Earth is made, and it is we know of the basic structure of Earth, that there is a solid core inside at the center of the Earth, and then there is a liquid outer core. Okay, having a molten lava, and then mantle, and then we say that of mantle there is the crust. Okay, Earth crust. So crust is almost 100 up to 100 kilometers thick. The very top portion of the mantle is normally it is considered earlier it was considered that the mantle is solid. Okay, but later it was found that the topmost portion of the mantle is in plastic state. It is not liquid, of course. These plates are floating over this, and they are continuously moving. They are continuously moving towards other directions, as Indian plate is moving towards north, towards Himalayas, towards the Eurasian plate. If you see this left picture, if you follow my cursor, this is the Indian plate shown by red is going up towards the green, which is the Eurasian plate. Okay, and this movement, this collision here at this line, at black line, causes the major earthquakes in this region. Okay, how these plates move? These plates move over this astrosphere, which is almost in a plastic state, not in liquid state, but in plastic state, and they are moving over this and causing this earthquake. And you will be amazed to know that the movement of Indian plate at near the location. If you have visited Uttarakhand, then you must be knowing the places like Nainital and Dehradun. They are very famous places. So that Dehradun is almost moving with a speed of 28 millimeter per year towards north. Okay, 2.8 centimeters per year towards north. So when this Korka earthquake occurred at the time of in 2015, shifted by some distance from its actual location due to that earthquake, due to the movement of this plates. So why this earthquake comes? When these plates are moving towards each other, and due to this movement, lots of strain is developing at the junction of these plates, and that stress, when that stress is released, the earthquake occurs. Three kinds of plate movements. The major three kinds of plate movements. The first is divergent boundary. Divergent boundary, where two plates are moving away from each other. Okay, they are moving away from each other at these locations. At these locations, now volcanoes appear, and lots of lava comes out. The divergent boundary is one thing. Then there is convergent boundary, which is happening in India. The Himalayas are forming due to convergent boundary. Himalayas are forming due to convergent boundary. You can see that the one plate is moving downwards and downwards to the other plate. The same thing is happening with the Indian plate. Indian plate is going subsiding below the Eurasian plate, and due to this, a lot of stress is accumulating at this juncture where this is going down. Okay, this due to this, when this strain is released, when this strain is released, this release of strain causes the earthquakes. Another kind of boundary, which is transforming boundary. Okay, in transforming boundary, what happens is the plates move sideways. They move sideways. You can see that location near Gujarat in India. In the left, if you see this map, the leftmost portion is Gujarat, and leftmost portion is India. The left portion is transforming boundary, which is the whole plate is moving upward. So side portions must be going parallel to the plates which are close by. So the earthquakes which occur in Gujarat are due to transforming boundaries, and the earthquakes which occur in North India are majorly due to convergent boundary. Now, why they thought that there is something like this plates? Why they thought, how they got the idea? Means it's a very wild idea. Per se, it's a very wild idea to think that Earth is broken into 7 different plates and these plates are moving. In 1900s, now they are GPS instruments. We can, if we regularly track the coordinates, then we can actually find out. Even when I told you that 28, the Dehradun location is moving by 28 mm per year, this is by some GPS studies done by different research institutes in India. How they got this idea? When they people started instrumenting the world by using earthquake instruments, the instruments to record earthquakes. They found that the epicenters are located in fixed locations, and these locations are normally concentrated near the lines, near these lines. Something must be going on in this at these locations, because each and every earthquake is coming near these lines only. They are not going anywhere else. So that's why they got the idea. These yellow dots, these are the earthquake epicenters. And you can see, if you look into a map which has earthquakes of last 100 years, you will find that in a regular band where all the earthquakes are concentrated. So they from this they found out that when the most of the earthquakes are concentrated in a particular zone, and that means that something is going on there. Okay, and that's why they got the idea of this plate boundary thing. So there are some more incidents which gave this idea, but due to time constraint, I am not going deep into that. Then they studied it more and then divided it into different plates. So the most famous plate boundaries which are one is this Indian and Eurasian plate boundary. Another is this Pacific plate boundary, which is also known as Ring of Fire. Why Ring of Fire? Because the biggest earthquake ever occurred are in this in the Ring of Fire. Ring of Fire, the Japan, the Cuba, Southern America, and Northern America. All these locations comes in Ring of Fire. Okay, that is in Pacific plate. This last big earthquake, which is the Cuba, which occurred in Cuba, I think almost 9 magnitude. In 2011, there was an earthquake in Japan, which was March 2011, I think. That was also 9 magnitude earthquake. The Pacific plate, the boundary of the Pacific plate is known as the Ring of Fire, because most big earthquakes occur at this place. This is the basic things which we should know about the earthquake. Now, the terminology which classify the earthquake. First is the earthquake. Earthquake is a sudden motion or vibration produced by rapid release of stored energy, as we discussed. Now, what is epicenter? You might have heard a lot of time epicenter. Okay, in Hindi you will say kendra. Okay, what is this epicenter? There, the earthquake started at some place which inside the earth. That place where the rupture started, considering it as a point source, the rupture started. That place is known as hypocenter, or the focus. Okay, where the whole event started. The closest point, just perpendicular above at the surface of the focus. Okay, the closest point at the surface of the earth from the hypocenter is known as epicenter. Okay, so epicenter is at the surface, hypocenter or the focus is inside the ground. Focus is the point where actually now, another thing is intensity and magnitude. When people talk about that, the earthquake was 7 in Richter scale or 6 in Richter scale. What they mean by that? So what they mean by that is the magnitude. Magnitude means the total amount of energy released at focus when the rupture occurred. Okay, what kind of bomb you blasted, and you will be amazed to know that a 6 magnitude earthquake is almost equivalent to Nagasaki nuclear bomb, which was dropped by USA in Japan after the Second World War. So a 6 magnitude earthquake, the energy released in the 6 magnitude earthquake at the focus is equivalent to Nagasaki bomb. And this magnitude scale is a logarithmic scale. So when we talk about the 7 magnitude earthquake, just one scale above, then we mean that the energy is 30 times. So when I'm saying that a 6 magnitude earthquake, I'm talking about 1 Nagasaki bomb. When I'm talking about 7 magnitude earthquake, I'm talking about 30 Nagasaki bombs. And when I'm talking about 8 magnitude earthquake, I'm talking about 900 Nagasaki bombs. So that is the way the magnitude, the energy increases with each magnitude. It's just not 1 point above. it is 30 times bigger. As similarly, 8 magnitude earthquake is 900 times bigger than 6 magnitude earthquake. Now, another point is intensity. Intensity is what a person felt. What a person felt. If you blow a bomb in Diwali, a person who is sitting inside the room might not hear the voice so loudly. Okay, a person who is close to the bomb will hear the voice much more louder. Okay, intensity. This the sound, the volume which you heard is intensity of the bomb. The size of the bomb is the magnitude of the bomb. Okay, so intensity depends on the person, its location, its distance, and a lot many things. So you must not confuse between intensity and magnitude of earthquake, and many people do. But I hope after this session, you must be clear with the intensity and magnitude of the earthquake. Now let's understand what a typical earthquake record has. The typical earthquake record, when earthquake started somewhere in past, and when this earthquake record is, let's say this earthquake record is of a place, let's say Delhi. Okay, and the earthquake occurs in Uttarakhand. So after some time, after few seconds, when the actual rupture occurs, the earthquake waves reach Delhi, and this is the point at around 2 seconds. The first wave which arrives are P waves. That's why they are also known as primary waves. And primary waves are compressional waves, just like sound wave. They are compressional waves, just like sound waves, have a longitudinal motion. And then after P waves, S wave arrives, and that's why they are known as secondary waves. They arrive after the primary waves. That's why the name S wave, secondary wave. The another feature of this S waves are shear waves. They move by the action of shear. The wave motion and the direction of propagation are perpendicular to each other. In case of P waves, the direction of propagation and wave and particle motion are in the same direction. Okay, and S waves velocity is much slower than P waves. For Himalayan region, it is around for P waves it is around 5 km per second, and for S waves it is around 2.5 km per second. So the time difference between S and P also gives us the distance of epicenter from the location where we are recording this earthquake, and that gives us the epicenter distance. And by calculating the distance from different locations, we can triangulate the actual location of the epicenter. Then comes the surface waves, which are the last, which comes at the last, and they are the slowest. And surface waves are not the original waves which started at the point where rupture occurred. They start when this P wave and S wave comes to the ground, and due to the interaction of surface and the primary and secondary waves, which are also primary and secondary waves, together are known as body waves, because they travel inside the body of the earth. And when they arise at the surface and they interact with the surface, these surface waves are generated, and they only travel at the surface. You might have heard that there are two kinds of surface waves. One is Rayleigh waves, and another is Love waves. Okay, these are the three kinds of major waves which we can see in a seismogram. Okay, let's go ahead and let's come to the geotechnical earthquake engineering. This is up to this we were talking about the earthquake engineering. Now, not earthquake engineering, but engineering seismology. It's all seismology. We were understanding the hazard. Now we will understand the engineering. Okay, so let's say this is the location where the fault was, and there the rupture occurred. So the wave propagated through the media. This is the rock structure inside the earth, and to the crust, the waves propagated, and when they encountered the superficial layers of the earth, the softer layers of the earth, soil. Okay, whole nature of the waves changes. This change causes a lot of damage, and this needs to be studied in detail. And this effect is also known as local site effect. Okay, what are the different kinds of geohazards due to earthquake? You can have landslides, you can have liquefaction, subsidence and lateral spreading, amplification of ground motion due to local site conditions, causing localized damage known as local site effects, which we discussed earlier. Okay, so these are the different kinds of geohazards which can be caused due to earthquake. Take up the landslides. These are the basic. This is an example of landslide due to landslide which is stable in normal condition. in static condition, but when vibration occurs, those vibrations may destabilize the whole structure, and due to destabilization, landslide may occur, and a landslide may cause huge damage. You can see here in the right picture. This picture is from the Kobe earthquake of 1995, that is in Japan. And in this picture we can see the building is hanging over the scarp of landslide, and this building is of no use now. Okay, and this landslide killed 30 people. Earthquake didn't kill the people, the landslide killed. Actually, the landslide killed the people, not the earthquake. Earthquake doesn't cause any damage. If earthquake comes in desert where there is no building, there is no damage because there is nothing. But the damage occurs due to different damages like landslide. This landslide caused 30 killing, and the building, the structure may have collapsed. That also could have caused damage, the casualties. Okay, so this is aspect of the damage hazards which can occur due to earthquake. And we should study how to stabilize the slopes for earthquakes, for dynamic loading, because earthquake loading is a dynamic loading, it's not a static loading. Okay, it's continuously changing with time. So we should study how to stabilize a slope which which should be able to take a load, dynamic load, and it will not fall, it will not fail. Now comes the liquefaction. In your geotechnical engineering course in civil engineering, you must have studied about the consolidation, and in consolidation you must have seen this. You must have studied this picture, where given by Terjaghi, this model given by Terjaghi, where the load is applied in box which is filled with water and provided with a spring. And as soon as the load is provided at the start, when the valve is closed, the whole load is taken by water, and there is no compression of spring. As soon as we allow water to dissipate, slowly water dissipates and the load is transferred to the spring, and the excess water gets dissipated and the spring compressed. Okay, and the whole load is taken by the spring now, and there is no load on the water. Now, this whole process for the soil takes a long time, maybe many years. Okay, but in case of earthquake, what happens is this whole thing occurs in few seconds. Huge load comes on the soil, and that huge load is very sudden and very instantaneous. It is completely taken by water, and due to that, the soil loses its effective stress. Okay, so due to loss of effective stress, you must have studied this equation, that is tau is equal to C plus sigma dash tan phi, and sigma dash is sigma minus U, where sigma is the total stress, U is the pore water pressure, and the sigma dash is the effective stress. For the soil, which this C factor, like clay, okay, clays have the C factor, but like sand doesn't have the C factor. Okay, in these soils does not have cohesion. So as soon as the sigma dash becomes zero due to increase in pore water pressure, the tau becomes zero. Coarse grain soils, the sand C is zero, so sigma tau is sigma dash tan phi. And in dynamic loading condition, as I told you, due to sudden loading, this sigma dash becomes zero. Okay, due to increase in pore water pressure, sudden increase in pore water pressure, because the complete load is taken by the water, and due to sudden increase in pore water pressure, the sigma dash becomes zero. And as soon as sigma dash becomes zero, the tau, the shear strength of the soil, becomes zero. And as soon as the shear strength of the soil becomes zero, it is incapable of taking any load, and building topples, as you can see from the picture, from the picture in the right hand side, which is from 1964 Niigata earthquake. Okay, this is a very famous example. You can see this picture in any textbook, very quoted a lot of time. Whenever somebody talks about the liquefaction, he will show this picture. Okay, you can see that the buildings which are in the front are not damaged. Even the building which are toppled are not damaged. The structure is not damaged. It is just toppled because the soil beneath the building is not capable of taking the shear. It is not capable of taking the load because the shear strength became zero. So this is the whole concept of liquefaction. These are the pictures from Gujarat. from 2001 earthquake, where this liquefaction was seen at lots of locations.